I've been in this field for over 30 years, interested in clinical trials, and that's why I'm the instructor for this short workshop. And my experience teaching is I teach graduate students and biomedical trainees, everything from introductory statistics to advanced statistics, and I also collaborate in a variety of research projects. The next slide, I think we got the introductions here, so we'll just pass along here. So learning objectives, these were posted on the website as well. I think one reason you signed up for the course is workshop is because you saw these learning objectives and thought, oh, well, this is for me. So more or less going through what I consider an introduction to statistics, going through descriptive statistics, what are they, how to summarize continuous data with appropriate descriptive statistics, different methods. There's a lot of misconception, misunderstandings, misuse of statistical methods among my colleagues, among the literature, so we'll try to straighten those out. Introduction to confidence intervals, what they are, something that's very common in clinical trials, p-values, and I'll be using the student's t-test as an illustration because a lot of times you may already know, since you work in the clinical trial field, that a p-value less than 0.05, okay, yeah, p-value less than 0.05 is significant, p-values greater than 0.05 is non-significant, but where do these p-values come from? How else is there to interpret them besides this dichotomy of significance, non-significance? We'll be going through that. And then going through some statistical terms used in clinical research, and then also some tidbits about how to interact with statisticians. Okay, so start off, what is statistics? And I had to go to a dictionary, Encyclopedia Britannica here. The science of collecting, analyzing, presenting, interpreting data. Very, like I say, classical definition of statistics, and I'm going to start unpacking what these words actually mean. All right, so more context. What we use statistics for is to summarize data and to make decisions. So within the context of a clinical trial, you want to summarize the results, saying if you're looking at a particular drug, you want to look at, say, what % of the patients who received the drug later on were spared, say strokes or heart attack. I will be focusing on cardiovascular disease, some of my discussions, so we'll think about strokes and heart attacks. And then also, to make a decision, you often leave it up to the FDA to make that decision for you, is whether or not the drug's approved or not. So statistics are used both ways for summarizing data and for making decisions. So for a few examples here already mentioned, does the new drug device therapy work? My materials not only focus on drug therapy, but also device and all type of other therapeutics. Are the two groups being compared the same or different? We consider that. So table 1. Every clinical trial has something called the classical table 1, which is a summary of the participant characteristics in a clinical trial. And so sometimes statistics are used to compare, what they call baseline differences or baseline imbalances. Also, diagnostic tests. For example, classic example is COVID tests. There's new versions of COVID tests being rolled out all the time, and you want to ensure that the new tests are just as good or better than the old tests. And then also, not only are we interested in the effectiveness of therapeutics interventions, but also identifying characteristics that increase the risk of disease. The reason for doing that, when you're planning a clinical trial and you have inclusion-exclusion criteria, you may want to select participants who are at higher risk to provide participants who are at higher risk of having a condition are more likely to have the outcomes, so you may wish to identify these characteristics. Most of the time, the identification of risk factors is done after clinical trial to see, in planning in the next one. One of the common misconceptions, which I see kind of thrown around both among my colleagues and also in the literature, is population and sample. Many times you'll be reading an article and they say, we study our population, our trial consisted of a population of individuals between the ages of 18 and 74, and 50% were male and 60% were of white race. And they'll use the word population as if they studied everyone. the clear distinction I want to make here, and this is very important when we start looking at test statistics, is a sample and a population. Samples. Every clinical trial that's ever been done has been done on a sample of individuals. It's never done on a population. So whenever anybody refers to a population in a clinical trial, they're mistaken. It is truly a sample, and we'll be looking at several examples of samples. So one example we'll be looking at shortly is a study that was reported in the literature that showed that taking low-dose aspirin can actually prevent heart disease and cerebrovascular disease. And there are currently 160 million women in the United States with heart disease. That's the population. We can't study all 160 million women in the United States in a clinical trial. And so this clinical trial took a sample of 39,876. That's a very large number of women in the study, but still, it's still a sample. It's still relative to 160 million, 39,876 is still a very small percentage. Now, before moving on, I'd like to make a clear distinction between the type of statistics, and again, there's sometimes misunderstanding or mixing up of terms. There's something called descriptive statistics and also inferential statistics. Descriptive statistics can summarize data, estimate, display, but does not test statistics. So whenever we talk about this, first of all, and say reporting clinical trial, many statisticians will provide a summary of descriptive statistics, meaning things like average age, percent of men and women in this trial, the breakdown of race, ethnicities, and different clinical characteristics. Those are purely descriptives. They're making no inferences. Inferential statistics is about testing hypotheses, making decisions. From descriptive statistics, you can't make any decisions. If you want to make decisions, you have to use something called inferential statistics. That's where you test hypotheses, you rule out chance, and that's a p-value, ruling out chance. You can also generalize from a sample to population. So that's why I made the clear distinction on the previous slide between a sample and population is you take a sample, you draw a sample from the population, which essentially, your volunteers, and then you conduct your clinical trial, you analyze your data, you do some inferential statistics, and from those inferential statistics, you then generalize back to the population. There are very few trials out there that are really interested in knowing if the intervention works on their small sample. What you wish to do is take the small sample of patients you have in your clinical trial and be able to generalize the results to everyone. And of course, also, inferential statistics is used to derive prediction models, meaning identifying risk factors that increase or decrease a person's of having an outcome. Okay, so here's an example of what I call classical table 1. I like to call it table 1 because every single clinical trial has one nowadays. And of course, every single clinical trial has a figure 1 as well. Figure 1 is your concert diagram that's required by these mainstream journals, but table 1 is essentially a descriptive summary of the patient characteristics. Notice that there's no column for p-values or confidence intervals. It's purely descriptive. And again, you look at it descriptively and say, do the groups differ in any particular way? So here's the randomized trial of low-dose aspirin in preventing cardiovascular disease in women. And of course, the 39,876 women in this study. Half of them were randomized to aspirin, low-dose aspirin. Half of them got a placebo, double-blind, randomized trial. And basically, randomization works. We often talk about randomization works by looking at the baseline characteristics. And you notice that the average age between these two groups is about 54, 55 years old. Percentages by breakdown by categories about the same. 60% are between the ages of 45 and 54. About 13% are current smokers, and the body mass index is about 26. So we're looking just at this table, we'd say that the two groups are balanced in terms of their baseline characteristics, which we expect to see in a large clinical trial. Now, an example of inferential statistics is as soon as you see the word p-value, you know you're in the realm of inferential statistics, as well as confidence intervals. Okay, both of these concepts we will look at in a bit more detail, but in terms of the classical Table 2, Table 1 is your baseline characteristics, Table 2 is your primary outcome results, and Table 3 might be your secondary outcomes, and then you have your table of adverse events. So here we have p-values, confidence intervals, and of course the results. So does taking aspirin lead to better outcomes? Let's have a look. Well, very easy to look at, and you don't need a lot of statistics. And again, sometimes common sense is the best way to look at the data. So when you look at the sample size, which is labeled as n, you notice that the sample size are approximately equal in both groups. So we don't need to do any complicated statistics, and we just need to look at number of events. We don't need the percentages because the groups are equal. And we notice that for ischemic stroke, women who got the aspirin, 170 of them had an ischemic stroke compared to 221, and therefore, yes, for preventing ischemic stroke among women who are at risk of having a stroke, low-dose aspirin is effective. The same goes for, down the road, you can see hemorrhagic stroke, a bit more likely among women. So again, we know that aspirin causes bleed, so it's not surprising that the hemorrhagic strokes will be slightly increased. Makes perfect sense. And then basically in terms of fatal strokes, not big difference. In terms of MI, not much activity in the MI, because you notice that the two groups have about the same number of outcome events. Again, very basic, looking at descriptively. I don't need p-values to know that taking low-dose aspirin in women, you can reduce essentially all types of stroke except hemorrhagic stroke because that increases your bleeding. But in terms of preventing myocardial infarctions, heart attacks, fatal and non-fatal, not a big difference. Okay, so for our first interactive exercise, okay, a pharmaceutical company wants to know, does the new vaccine prevent illness compared to placebo? So what do we do? Is this a descriptive statistics question or inferential? Yeah, exactly. Okay, it's inferential. We want to know the differences. Great. Okay, next one here. Okay, medical device company wants to know, does the new catheter decrease post-operative times after surgery? Inferential or descriptive statistics? Okay, both have great. Inferential statistics, again, we want to know, is there a difference? Last one here. A government agency wants to know, what is the prevalence of cardiovascular disease among women? Descriptive statistics, yeah, exactly, yeah, descriptive statistics, because we do not want to make any inferences or make any decisions. All we want to know is, what is the prevalence of cardiovascular disease? Great, okay, so far so good. Okay, so 4 types of data statisticians juggle with. The reason for showing you this is because the type of data then drives the type of analyses. Certain statistical methods are used to analyze nominal data, ordinal data, discrete data, and continuous data. 4 different methods. Again, over my 30 years of collaborating, teaching graduate students, I see mistakes made time and time again. And one of the things you might see on some protocols, in some protocols have tables where they describe both the data instruments they're going to be using to collect the data, but also what are they? Is the instrument going to provide you nominal data, ordinal data, discrete data, or continuous data? Because that really helps the statistician like myself to then to say, okay, if it's nominal data, I will use this method of analysis. If it's continuous data, I will use a different method of analysis. Okay. So for example, the 4 types we're interested in nominal, and essentially are nominal as in Latin, from the Latin word. Nominal is from the Latin word name, in name only. The categories are not ranked, they're interchangeable. Hair color, gender, blood type, hypertension status. There's no ranking, there's no ordering. Ordinal data have a natural order. Glasgow Coma score, severity of adverse event, mild, moderate, severe, satisfaction scale, something you'll be filling out in your survey after the course to get your credits, a satisfaction scale with this course. It's going to be an ordinal scale. There's a natural ranking, meaning severity, mild severity is a lot better than having severe severity. Okay, so there's a natural order. Discrete, this is where people make mistakes here. Number of children, number of survivor, bacteria counts, number of children. Sometimes you see in the lay press, the average number of children the families currently have in the U.S. is about 2.3. You often get asked the question, who's the third of the child? That's plain silliness to have same thing, bacteria counts. Sometimes you see reports of bacteria counts that say the average bacteria count is, such and such and have decimals. You either have a bacteria, you don't have bacteria. There's no such things as partial things. So discrete are a very special type of, they look like continuous, but they are all integers. Okay. The last one here is what we're most familiar with is continuous data, which are real numbers. They actually do allow decimals, the average weight, average age, average degree of stenosis, meaning narrowing the artery, and of course physician salary. Yes, they all have dollars and cents, and therefore decimals are allowed so that it's a continuous variable. Now, so here's an example, just sort of mapping out these definitions onto reported data. So we have age. Now, if I said, well, we're going to ask every patient who enrolls in a clinical trial their age, and is it continuous or can it be something else? Well, yes, age can be continuous as recorded. So the average, person gives you age and say they give you a date of birth. If they give you a date of birth, you can actually calculate their age to nearest day, and therefore convert it to a decimal. So like in here, 50. So the average age is 54.6. But you can also categorize it into an ordinal variable, into 45, 54, 55, 64, and greater than 65. So age can be both continuous and ordinal, depending how it's actually reported. If you give me age as continuous, I'll be using one method of analysis. If age is then categorized as an ordinal variable, I'll use an entirely different analysis. Okay, so understanding the differences between the types of data is very important to guiding the type of analysis that statisticians will do. Smoking status, current versus past never, is nominal. Okay, it's interchangeable, although some could argue that a current smoker is worse than being a past smoker. So again, it's nominal, could be ordinal, depending on whether or not you want to apply a risk to it. So for example, the risk of lung cancer is much higher among current smokers than past or never smokers. So essentially one could be treating smoking as ordinal, but because it's only two categories, we often treat it as nominal, interchangeable, and we also have a special word called binary. Or dichotomous or binary is what statisticians use when there's only two categories in a variable. Body mass index is like age. You can calculate the body mass index as a mean or the average, as well as you can reclassify it into different categories, which is the levels of obesity. Okay, so just a refresh here, just a review here. Study wishes to describe birth characteristics in a population. What type of data are birth weight? Yeah, great, continuous. Okay, so we have birth weight in grams is continuous because you can always measure birth weight to a decimal place. Suppose now we have birth weight, but now it's being categorized into small, appropriate, large for gestational age, which is often how it's classified in medical charts. Okay, we have a continuous, you have an ordinal. In this case, yes, birth weight was originally classified as continuous, but in this case, if you look at the medical charts, if you have small, appropriate, large for gestational age, in this case, this variable would be then ordinal, and they'd be analyzed. If I had this in front of me, I'd have to analyze this as ordinal data because the original birth weight, the actual grams, is now being stripped away from these data and recategorized into these 3 categories. Okay, a study wishes to describe birth characteristics in a population. What type of data are the type of delivery? Cesarean, natural, induced. Okay. Okay, we have it. Ordinal, we have, okay, so we have continuous, oh, nominal. Okay, so continuous versus nominal, again, cesarean, natural, induced, nominal, they're interchangeable. Just to refresh, continuous, it can't be continuous because there are, often you think of continuous as being having some sort of units, like age has years, birth weight had grams, hypertension has millimeters of mercury. Because these are just words, cesarean, natural, induced, 3 categories, it is nominal. Now, some could argue it's ordinal because depending on, if you now apply or assign type of, say, pain of delivery, you might find that induced might be more painful than natural or cesarean, and some might consider as being ordinal. But in this case, if I was analyzing these data, I'll be analyzing them as nominal data. So in terms of where we're heading in this short workshop, graphs, estimates, and statistics, inferential statistics. 2 types we're looking at for continuous and categorical, making that split there. So first of all, we're going to start off with some graphics and plots, distinction between box plots and histogram. Again, just going to dispel some misconceptions that I see among colleagues and my students here between a box plot and histogram, and also what a bar chart is. We'll be looking in a bit more detail about what mean, standard deviations, median, interquartile range are, mode and percentile total, which are commonly reported in every single clinical trial. And then as far as inferential statistics, look at the t-tests in much more detail, derive confidence intervals and p-values, and do briefly look at what analysis of variance is. Some more common methods you'll see in clinical trials: analysis of variance, a linear regression, chi-square test, logistic regression, and survival analysis. So we'll be covering these in mostly in both the t-tests in great detail, and the remaining ones we'll be looking at those briefly. Okay, continuous data appropriate statistics. 2 ways of summarizing data with descriptive statistics. One way is in a table. Okay, so here we have a nominal variable menopausal status after the use of hormone replacement therapy, premenopausal uncertain, postmenopausal and current HRT, and postmenopausal and no HRT. And what's often presented in a table like table 1 is a percentage of the participants in a clinical trial that were in each of those categories. So what we see here is that 27.6% of the women in this clinical trial were premenopausal, 18% were uncertain, 30% were postmenopausal and were on current hormone replacement therapy, and 24.4% and were postmenopausal and were not on hormone replacement therapy. Now, this is great. This presentation is wonderful for a report because you have an opportunity to look at these, to study these numbers, and to make sense of them. When it comes to presentations, this is useless. There's countless number of times I've seen people present data, for example, where essentially what I did here is copy and paste a table from a report or from a published literature of a clinical trial and say, okay, here's the baseline characteristics of these participants, and you and the audience are saying, wow, these numbers are just overwhelming. I have so many numbers, I can't make sense of it. The best way to present numbers at a presentation is not showing a table, but showing a graph. Okay, so the first one I introduce you is to a bar chart. Bar chart is essentially a re-representation of tabled numbers. So for example, these numbers you've seen in the table, 27.6%, 18%, 30%, and 24%. All it's reporting is the percentage of participants in each of these categories. This is the most effective way at a presentation to show the results. Tables, believe me, my advice is absolutely useless. So if you have a statistician that's provided you some results and it shows tables and numbers, and doing presentations, tell them, convert them to figures. Pictures are much more effective. Now, also, if you're working with statisticians, there's a lot of white space. One of the things I've seen throughout my years is people will not report. So what they'll do is, so essentially what I'm trying to do here is, I can use this, there we are. Okay, black it out here. And you'll see this many, many times, is people will report bar charts without any numbers. And so you as the audience or a viewer will look at this and rather than focusing on the message, you're fixated on wondering what the numbers are in this bar chart. And what I tell my data analysts is select an option in your program to print out the numbers above, right? Do not frustrate. My main message is do not frustrate your audience. Audiences are so easily frustrated by being fixated on trying to figure out what that number is. And given there's so much white space on slides, put the numbers above it. Don't, put all the information up there. Don't get. So anyway, that's my advice when working with statisticians. Notice that, from this figure, you can easily see that the highest percentage of patients had postmenopausal and on current HRT, followed by premenopausal. And it's a lot easier than trying to discern that information from this table. Okay, yes, it is clear from 26, but there's a lot of other numbers going on. And a single figure basically summarizes beautifully. Also, when you're comparing two groups descriptively, use bar charts. Again, there's so much white space. Like, only by white space is all that stuff, the white space around the bars. Put the numbers above it. Okay, don't. You hear me again, saying again. Don't frustrate your viewers. Okay, keep your audience happy by actually putting all the numbers on top of the bars, and you can actually see the visuals there, right? Two color bars. Here we are comparing percentage of older persons with sensory impairments to persons who are younger, so older versus younger. So my younger group is between 70 and 79 years old. The older group is 80 years and over. Two very distinct colors. The other thing is the color choice. I've chosen colors. These two colors are accessible to people who are colorblind. 7% of the American population are colorblind. Most slides are not colorblind friendly. Many people love to use blue and red. For a colorblind person, red is black. So you put a red bar besides a black bar, and all they're going to see, 7% of your audience is going to see black. So again, thinking about how to present your slides, use colors that are colorblind friendly to include the other 7% of the population who are colorblind, as well as putting the numbers goes a long way. And also choose colors that are contrast. Okay. Now, most people would say this is a bar chart, and it's not. It's called a histogram. Bar charts are used for nominal data and ordinal data. Histograms are used for discrete data and continuous data. The distinction here is, if you look at the other slide here, the bars do not, except for the groups, the bars do not touch. Okay? The four different categories are separated by spaces, and that's what defines a bar chart. A histogram, all the bars touch because it mirrors the continuity. When we talk about continuous data, we're talking about continuity, meaning there's no breaks in the data. Okay, so here we have a distribution of cholesterol levels among elderly patients, and it basically shows you the distribution. Now, the reason people call this a bar chart is because you can actually see above this bar here there's 106 patients, and of course you can always put the numbers above that but here the numbers would be too small to look at, and so we just basically don't bother with the numbers here. But anyways, bar charts, the top of the bar here, 106 patients between 5.25 and 5.75 millimoles. Histograms are plotted the same way as bar charts by stats packages, but the bars do touch because it's representing continuous data. Now, the other thing histograms are very good for is identifying something called extreme values, or other people call outliers. So I noticed that most people have cholesterol levels between 5.25 and 5.75 millimoles per liter, and then we have a couple of people who have very extreme values. One easy way to identify these extreme values is graphically is using histogram. It'd be very difficult if you can imagine an Excel spreadsheet with 574 records, 574 rows. It'd be very difficult to find these two numbers in it. A histogram is a quick and easy way to display the distribution, including identifying extreme values and outliers. Summary statistics, average. We all learned about averages in public school. And the way averages were taught to us, the way they're taught to me, is you take a bunch of numbers and you divide by the sample size. So in this case here, we have 10 numbers, and what you've never been told, I've yet to meet a person who's been told this, is the average. The reason why average is so popular, or we call in statistical terms the mean. Okay, so mean and average are synonymous, so people call it average for the sort of the lay public, and in sort of more technical terms, we call it the mean score, the mean value, as in the other table 1, we saw the mean age. And so we have 10 observations. And what I've displayed here is that I put down all 10 observations on a balancing beam. So I have a measurement of, at 4, I have 2 measurements at 5, 1 at 6, 2 at 8, 1 at 12, and 3 at 14. So if you add at 4 and 2 5s, 1 6, 2 8s, 1 12, and 14, and divide by 10, you'll get the average of 9. That's the mean. What many people don't know is the mean is a center of gravity. When you talk about measure of center of tendency, that's a center of gravity. So when you put these tiles on a balancing beam, the balancing beam will only balance at one point, and that point is 9. If you put another tile here, if you shift the tiles over, the mean will also change because it rebalances. Yes, mathematically, it's still adding up the numbers divided by the sample size, but the key feature of the mean is it always balances on the mean. Okay, the balancing beam is always balanced on the mean, and that's the center of gravity. Now, the median is something else you'll see, and that's the middle. It's unaffected by where you place the tiles. It's always going to be the middle value. So in this case, the middle value is 8. You have 10 tiles. Let's count them out. Okay, there's 1, 2, 3, 4, and then 5. Okay, so I have 5 going this way, and I have 3 here, 4, and my 5th tile is also sitting at 8. So that's my median. The median is always the middle number on an ordered scale. The last one you'll see reported in literature, people do report this, is something called the mode, and that is just the most common. So we have 3 tiles sitting on 14, so the mode is 14. So all 3 measures are considered to be measures of central tendencies. They're trying to get that, and what I mean by central tendency, that is the single number that best describes all your data. So the mean could actually, the average age, when we talk about the average age is not only the center of gravity, it's not only just the sum total divided by the sample size, but it's also the single number that best characterizes all your data. So when we report the average of the mean of 9, we're saying 9 represents all 10 numbers. If we report the median, we say 8 is our best guess at representing all the 10 numbers. And if we choose the mode, then we say that 14 is the single best number that describes all 10 numbers. So the whole idea behind statistics is to basically to reduce the data into either single numbers or single diagrams. So the mean is the single number. So here's an example, a little tricky one. The mean is sensitive to values that are very large or very small. Okay, the median's not. So again, thinking about why, and you may have heard that if you've taken a previous stats course, the mean is sensitive to values that are very large. Why? Yes, mathematically, but now you know the reason why the mean is sensitive. It's a center of gravity. If you add in very large numbers, you're shifting the center of gravity, and the mean has to recenter itself. The median is not affected by that. So here's an example, 5 Bostonian salaries. We have one person earns 30,000, another person 35,000, 50,000, 1 million, and 75,000. Which measure best characterizes? Okay, so this is an interactive exercise here. So we have 5 people. So which measure of central tendency best characterizes these 5 individuals? The mean or the median? Okay, so both have answered the mean. Okay, let's see. Maybe yes, maybe no. Let's break this down, because I think it should be the median. Because, again, what is the best measure? Now, you would say the average salary is $238,000. All 4 individuals would love to get close to that number. Okay, so you notice how the mean can be misleading. Okay, so you think about how many times you've seen the mean, which is the average, reported in the literature or report. How many times do you think about that? You've seen that. And how many times have you thought, could that mean be misleading? Okay, so in this case here, by selecting the mean, you're basically saying the single number that best describes these individual salaries is 238,000. Yet it's only one person that's making over 200,000. They're making $1 million. So notice how a single person can actually affect the average. Now, you notice that if you look to the median is 50,000. It basically represents, much better represents, okay, excludes the person who got the $1 million. But if you're looking for a single number, well, again, that's what the average is. It's a single number that's supposed to represent the entire group. And it could be misleading if there are extreme values. And so, again, how many times have you saw in the literature that, oh yes, here's the average? It could be misleading. And this is a good example of how an average can be misleading if you don't have a bit more information about the outliers or potential, large extreme values. Okay, so there's a natural ordering between mean, median, and mode, and what we call a symmetric distribution. Now, we'll be looking at this one in more detail. It's called the normal distribution or the Gaussian distribution. The mean, median, and mode are all the same number. If you have, now, most biological data, okay, laboratory data, biological data, genetic data, you name it, anything that's biological has a right skewed distribution. This is reality. This is what statisticians deal on a day-to-day basis, where the mean is larger than the median. Okay, so you think about what type of biological data I'm talking about. Blood pressure. It's biological. We can have patients who have blood pressures 200, 300 millimeters, and they're still alive. Okay, 200, 300 millimeters mercury, and they're still alive. But you don't find, for systolic blood pressure, but you don't find very many people who are alive who have systolic blood pressures below 40. Okay, they might have their diastolic below 40, but not their systolic below 40. So most of the data, like blood pressure, is going to be right skewed. Cholesterol levels is always going to be people with high cholesterol levels, glucose levels, serum creatinine levels, but you have biologically a lower limit. Okay, so the mean is always going to be larger than the median, and we have a positive skew distribution. On rare occasions, you might find distributions with what's called negative skew, where the mean is less than the median, but that's very rare. Like I say, the data sets that we use, biological data, are always going to be right skewed or positive skewed. Okay, so moving on, something called percentiles. You'll see this reported in reports and literature, and things like quartiles, or something more commonly, something called the interquartile range. You'll see that reported quite often. And that goes along with the median. So when statisticians talk about quartiles, they're equating to something called percentiles. So a first quartile is the 25th percentile, synonymous words. And what a first quartile means is that 25% of the observations lie below that number. The median we already defined as something called the 50th percentile. Again, what I find is the reason why people are frustrated with statistics is the jargon. Okay, so once you get over the jargon and think about what the function, then you're further ahead. Okay, so the jargon here, median percent. So statisticians throw this around all the time. We'll call this the middle quartile, the median, the 50th percentile. We use this in many, many different ways, and all means the same thing, which again, to a novice reader, it gets quite confusing because some reports can report the median, other reports can report the 50th percentile. And all it means is that the median is 50% of the observations lie below that number. And then we have another one called the third quartile, which is the 75th percentile, is 75% of the observation lies below that value. Now, how do you remember these things? That's easy. First Q, first quarter, right? If you don't like the word quartile, think of quarter, a year. First quarter, that's 25. And then the median is the middle, median, middle, that's the 50th. And then the third quartile, 3 quarters, right? 3 quarters, 75% of the observations, okay? So you think of more conceptually, first quartile is first quarter, third quartile, whether you like it in terms of money applications or sports games, right? Football has 4 quarters, first quarter, you know, and then they have the halftime show. I guess you can say halftime percentile, but a halftime. But you get the first quarter, midterm, you know, median, and the third quarter. Now, the way it's reported often is the interquartile range. So notice that we have the median of 16. This is measuring left ventricular outflow tract. So the median is 16. And just look at these numbers now. The first and third quartile, we know that 25% of the individuals had LVOT less than 7, and we know that 25% of the sample had LVOT above 26, right? You know, you can think of the symmetry. If it's 75% is below 26, then 25% of the sample is above 26. So we know that 25% of the sample is below 7 and 25% of the sample is above 26. So again, understanding what interquartile range is and what two components, you know, those two numbers represent, it's easy then to figure out what percent of the sample is below or above those numbers. Okay, now something moving on here. Again, recap. Means is the best guess. And you hear me say this one time. A mean is the best guess for representing the entire sample. Variability, some people talk about variability, standard deviations. You'll see that word used time and time again, standard deviation. What is that? Variability, what do we mean by that? Variability, number of coffee breaks taken during the day by 9 people. When people talk about variability, they're talking about distances, spread. Some people use a spread, your word spread. What's a spread of data? It's a literal spread. It means that here's the mean, here's the average, sits in the middle, and then coffee breaks. You all have colleagues. Some have 1 coffee break. Other colleagues frustrate you because they're always on a coffee break. Okay, so some have few coffee breaks, some have a lot of coffee breaks, and then the other people are kind of in the middle. It's called the spread. Okay, spread. Again, in statistics, we want to come up. We have 9 numbers here. What is the single number that represents all these 9 numbers, the spread? And that's called the standard deviation. Okay. Now, the reason I'm showing you this formula is exactly the point. Standard deviations, and you see that again in table 1, you report the mean, mean age, and then the standard deviation. The standard deviation is just measuring the average distance an observation is from the mean. A single number that represents distances from the mean. I'm showing you this formula because this is the observation. This is the mean. Okay? You don't need high-level math to look at this and say, okay, I'm measuring the distance. The difference between the observation and the mean is the distance. We square it because it doesn't matter if you take few coffee breaks or more coffee breaks, you're still taking coffee breaks. So we square it to remove, it doesn't matter if you're taking more or less. Then we have the summation sign. That's a fancy symbol in statistics, summation size, and of course we take the average divided by the sample size. Okay, so I'm showing you the formula to help you understand that when you see the phrase standard deviation, all that is, it's measuring the average distance an observation is from the mean. And then you start thinking about, wait a second, okay, standard deviations. Well, if the standard deviation number is very large, then you have a lot of variability, meaning that there's a lot of spread of observations from the mean. And if the standard deviation is a small number, then you say, oh yes, there's not a lot of spread in the data. Okay, so that's one way you can think about the standard deviation. Now, I love graphical displays. Okay, I love numbers, but I love graphical displays even better because graphical displays can actually present you numbers in very succinct ways. So one of the ways to represent, all this, medians, quartiles, extreme values is something called a box plot. Okay, it's something similar to a histogram in terms of what it can display, but it displays in a slightly different way. So we've already looked at a couple things here. The median, okay, which is the middle number. We saw the first quartile, which is 25% of the observations lie below that value. Third quartile, we're at 75% of the observations lie below that value. And then we have something called inner fences, and then of course for our outliers. Okay, so essentially we can use a box plot to display all these numbers on a single figure. You can only imagine if you had a table of all these numbers. It'd be very complicated. Okay, so when you're talking to a statistician or you're working with a statistician, tell them, look at all this white space. Use it up. What do you use white space for? Numbers. Okay. Most of the time when I see box plots, they don't have numbers. Okay. Why keep your reader guessing? There's so much white space. Put the numbers in there. So we know that the median is 5.76. That's 50% of the observations lie above and below that number. And of course, we have the two quartiles, the first and the third. And then these are very special numbers, something called inner fences. What inner fences represent? 99% of the observations. So 99% of all your observations lie between the inner fences. Okay, so 99% of all the observations lie in that space. And so if 99% of those observations lie inside the space, what that means is these are, as no political statement, as Bernie Sanders mentions, the 1%ers. Okay, these are the 1%ers. These are individuals that you would consider as extremes or outliers. Okay, and by this definition, and most commonly accepted, the 1%ers. Okay, this means that this represents 1% of your sample. And these are the individuals that will actually affect your mean. This is one way. This is another way. The first way is a histogram. Histograms are good identifying your extreme outliers. A box plot is even more effective because you know that within the red rectangle, which is the center rectangle between the inner fences, is 99% of the observations, and 1% of the observations lie outside those fences. And you can identify them very easily from a box plot. Now, besides identifying outliers and extreme values from box plots are even more effective when you want to compare groups graphically. So here's a comparison between men and women in terms of their cholesterol levels by age group. And it doesn't take a statistician or somebody who has high-level statistical backgrounds to basically see that among women, their cholesterol levels, okay, by age is less than 35, 36 to 45, 46 to 55, 55, okay, increasing age. It doesn't take a statistician to see that for women, their cholesterol level increases with age much faster than it does in men. Okay, in men, there's slower decline. It takes a very quick and easy way to see group differences using a box plot. Now, you already know, well, wait a second, you can also tell a lot of other things from a box plot besides the comparisons, because now you know where between the first and third quartile, 50% of the observations. Okay, so you know that 50% of the observations are between in that rectangle, and you also know that 99% of the observations are within the inner fence, and of course you can see the outlier extreme values. As I mentioned, most biological values, biological numbers, are right skewed. Okay, you notice the right skew, you have these extreme values out here, which are now identified. Okay, so you notice that so some men have higher values than women. So, as I mentioned, there's a one-to-one correspondence between a box plot and histogram. Okay, both are used for continuous and discrete data, and they both can actually identify your extreme values, outliers, and the shape matters. So, for example, the first one here is the most important. This is most biological data. You have a right skew. Some people use the word positive skew. Some people use the right skew. Again, jargon, I wish there was a consistent phrase that everybody used. But some people use the right skew. Some people use a positive skew. Same means the same thing. Has a long tail. Okay, this long tail. Now, how this manifests itself in this box plot, it has a long, what you call a whisker. Okay, the fence on the right-hand side, it's much longer than the fence on the left-hand side. Okay, so when you see a box plot with a long right fence, it means it's positively skewed. Okay. Here you have one that's symmetric, where the two fences are about the same. And then, of course, the one you have, the fence here is longer on the left-hand side. You know, it's left skewed or negative skewed. And again, you have to be careful. You may look at the box plot and say, yes, okay, it looks symmetric because the two fences are about the same length. But you have to be a good detective to say, oh, yes, it may be true, but you have these extra dots out here, which are the extreme values. And again, you notice how they're picked up in the histogram. Okay, you have a symmetric looking histogram with a few data points outlined. Okay, so this is essentially summarizing, you know, the one-to-one correspondence between a box plot and histogram, and the features you need to look at to identify whether it's right skewed, left skewed, and also, most importantly, are these extreme values and outliers. Okay, the last plot, and we'll be looking at this again later on, is something called a scatter plot. A scatter plot is used to describe the relationship between height and weight. We know as we age, we grow in height, and there's also correspondence with weight. It's not a perfect relationship, okay, but essentially it's called a positive relationship, meaning that as the taller the person, the more they weigh. Particularly true in children and adults as well. Adults mess it all up because we stop growing at a certain point, but we keep on gaining weight. But at least between the heights of 60 and 76 inches, there is a correspondence between height and weight. Okay, so each dot here represents the paired height and weight, and we draw a straight line called a fitted line or regression line, and that just basically describes a linear relationship between height and weight. Like I said, we'll be looking at this again a little later on, but I just wanted to throw that in right now. Okay, so interactive exercise. Looking at this diagram, so let me break it down for you. So we're comparing males and females. Okay, body mass index, kind of go along with the height example from a previous slide. So we have body mass index, which a measure of, it's a surrogate marker of called body fatness, you know, very loosely, but it's body mass index. We're comparing males. Males are in the blue color, traditional blue, and then females is more in the orange color. Okay. And just to throw in something else is we have comparing males and females, but then we have 2 years, those who are younger, less than 21 years, and those who are greater than 21 years. Okay, so who has the higher BMI? Okay, men and or women. Okay, I have men, yes. Okay, so good choices, good choices. Let me break down the answer here a bit. So, if you've answered men, okay, yes, that is true. Not particularly a trick question, but I guess thinking about this, yeah. Okay, for those who are less than 21 years old, absolutely true. Yeah, because we notice that two things are happening here. If you were to look at the mean, and this is one of the nice features about this box plots, the diamonds, yeah, the diamond is the mean, and the horizontal line is the median. So again, the mean is higher than the median. They're both right skewed, positive skewed. One feature, right? The mean is higher than the median. Now, it is true for those who are less than 21 years old, the men are higher than the women in terms of the means, in terms of the medians themselves, right? The horizontal lines, absolutely true. Now, when you look at the greater than 21 years, the means are about the same, and the medians are a little less for the men and the women. So it's not a trick question, but it's a question where it says it depends. right? So this is an example where it's not a clear-cut answer. One of the first things that frustrates most people with statisticians is my favorite phrase, it depends. A lot of things depend. So for those who are less than 21 years, you're absolutely right. Yes, men have higher BMIs than women, but individuals who are above 21 years, not much of a difference. Brief recap, what does the box represent? What I mean by the box is this thing right there, okay? That's what I mean. What does the box represent? What percent of the BMIs? Okay, everybody says 50%. Yeah, absolutely right. Okay, 50% of the BMIs are represented by the box. Now, in terms of 99%, yes. Okay, 99% is this distance here, right? There's these distances between the fences. That's 99% of the observations are there. But the correct answer here is 50% of the BMIs is the box because that is between the first and third quartile. Oh, wait, one more here. Okay, a bit more difficult here. Among a sample of 226 patients. So we have 226 patients. The mean, I'll just highlight a few things for you. Yeah. Okay, so we have the mean equal to 112. We have a median equal to 110.5. And then we have a mode. Okay, so central tendency. Which is the best number would you select? Mean, median, and mode. Okay, have one mean, have median. Okay. Okay, good. So they both chose median. Yes. The median is likely a good choice because, as you know, blood pressures have a right skew distribution, and of course, you might have some extreme values that might actually pull the mean towards those. Now, that being said, a bit of practical advice. The median. The median is a terrific number to report at a scientific presentation where everybody's basically taken some basic statistics and knows what a median is. Believe me, when you're talking to the lay public or a lay report, most people don't know what a median is. They might think a median in common language is when you're driving on the road, you don't cross the median. That's a center line, right? That you say the center line, you don't cross the median, the center of the road. So that's how most people understand a median. So if you talk to a lay audience and say the median's equal to 110.5, they'll think the center of the road is 105, 110.5. Okay? They won't understand. Yes, it is technically correct to report a median in this case. However, even the word mean, I use interchangeably with average, depending on who I am talking to. If I'm talking to my scientific colleagues, I will use the word mean. If I'm giving a presentation to a lay audience or the public, I will say the average. The average blood pressure is 112.2. So it's important to keep these words contextualized to whom you're talking to. Okay, just something to think about. Okay, so same question here. Blood pressure, again, mean is 112, median is 110. Is it negative, symmetric, or positively skewed? Okay, we have one is symmetric, one is positively skewed. Okay, let's break this down here. Okay, so based on the strict definition of mean and median, the mean is larger than the median and therefore is positively skewed by the strict definition. Again, thinking about, 112.2 and 110.5 doesn't make much of a difference. So if you think about the distribution, they're so close together, you're likely not having a lot of extreme values. Remember, the extreme values are moving the center of gravity. So if you have very large values, the difference between the mean and the median is going to be very large. In this case here, the mean and median are very close. And so, yes, technically, by statistical definition, it is positively skewed, but is it close enough to be considered to be symmetric as well? The next topic here in objectives is confidence intervals. Okay, so here's something that may be unfamiliar. Is when people do clinical trials, when I'm involved in clinical trial, we do things only once. I've done many clinical trials and I only do once. Now, okay, granted that for phase 3, in order to get your device is a little different, but in terms of drugs, in order to get your drug approved by the FDA, you need 2 phase 3 clinical trials that are both significant. Okay, for the orphan drugs, you only need 1. For example, the COVID vaccine would be considered kind of an orphan drug, and there's only 1 trial. Moderna did 1 trial, Pfizer did 1 trial, AstraZeneca only did 1 trial, but most of the time you need 2 trials, 2 different samples to actually get your drug approved. Device trials really don't need much of any type of evidence in terms of clinical trials. So we do things only once. And we rarely see the consequences of doing things once or twice. And we believe our study is large enough, and you hear statisticians quote this word, oh yes, we have 80% power to detect a significant difference, and you think, wow, our sample must be the truth. It must contain all the information. What we don't see is, well, what if we repeat the experiment? Now, the issue with the clinical trial, we don't repeat the experiment. We don't do the same clinical trial in the same population of individuals. We take a different population. Again, you want diversity. So you might do a trial that's US-based, and you might do a trial that is partly overseas and together with US, kind of a mix US overseas, because you want to have global marketing. So you have a strictly US trial. And then, of course, if you want to market in Europe, you may have to do another trial that is solely European. So it's a totally different group of individuals. Very rarely would you repeat a clinical trial twice in the same population in the United States. It'd be like, well, why waste? That's a waste of resources. Okay, you want to increase your market. So you do things only once. And what are the consequences? Well, here is an example of, it is hypothetical, it's simulated example, but it illustrates a point about what I want to consider about sampling variability. So what I've done here is, from my class, as I mentioned, I teach graduate students, I measure the BMIs. I had 16 students in 2000 and, I think it was 2015 here. Yeah, 2015, I had my students take the BMIs, brought the measuring tape, the scale, anonymized participants A to P, there's 16 students. That's my population. I only had 1 class that year. I had 1 class of 16 students. That's all I ever had in 2015. So it actually is, by definition, a population because it's everybody. And everybody in my class measured the BMIs. BMIs, as you can see here, range from 24 to 30. With the average BMI of 24.81. That is the true value. That's the population value, 24.81 with a standard deviation of 2.99. Okay, that's based on all 16. Okay, so that is the truth. Now, what we do in clinical trials, and I'm simulating clinical trial, is take samples, small samples. So suppose I take a sample of 8 students. What results do I get? Again, remember the first slides? sample, population and sample, the distinction I make there. So my population is 16 students, my sample is 8. Okay, so notice that here's my first sample of 8 students, and this is like a small clinical trial. A laboratory example, you know, if this is an animal study, eight rats would be a large sample. So we have eight students, not rats, but 8 students. And we have an average of 26. Okay, so based on this single sample, we have an average of 26. That's the average BMI. And according to my chart, I would say, okay, it fits in this range here. Again, 25 to 29. Oh, on average, my students are overweight. Okay, and say, well, no, I don't. They can't be overweight. They're young. Can't be. So I take another sample. And again, I'll get 26. Okay. 2 numbers in a row, 26, both match. Should I believe that? No. As I say, if you don't, you know, if you first don't succeed, try again, or third time's a charm. Third experiment, I get a different number. Oh, darn it, 25.4. I don't know. I got 26 on 2 tries, but they equal 25.4. I'm not sure anymore. They still fit in the overweight range. I'm going to do my experiment one more time. And so I do my experiment one more time. Average 23.8. Oh, let's look at the chart here. 23.8. Oh, that's normal weight. Wait a sec. My first three samples lead me to conclude that my students are overweight, and I get another sample that is normal weight. So I do it again. I said, okay, let's try this again here. Get another sample, and darn it, they're now overweight. I do another sample here, and they're normal weight. So what is it? You know, like 4 times, I do six experiments, 6 times in a row. 4 times it becomes overweight, twice as I don't know where it is. You know, I don't know where I'm going. Okay, how do we solve a problem? How is statisticians have solved this problem? Where you get, this is called sampling variability, meaning that every time you repeat your clinical trial in the same group, same population, you're guaranteed to get different results. And the results you get may be conflicting. That's why most of the time you want to do a trial only once, right? Pfizer and Moderna and AstraZeneca were smart doing the COVID vaccine trials only once, right? If you did it again, you might get a different answer. So do it once. Sampling variability. So how do we solve this issue? Let's recap here. Sampling. So here's a population, another large population, represented by a large histogram. We know at the population level it's 48 mean. Okay, so we use this statistical symbol mu, Greek symbol mu, for represent the mean. The standard deviation is 41. Sigma, the Greek letter sigma represents the standard deviation. So a mean 48, standard deviation 41. Very, very large sample size. That's our population. Say millions of individuals here. Now we take a sample. How does this look? Okay, so in the first random sample, there's our answer. I'm plotting this on a histogram. Okay, so you took the first random sample. There's the average. Sample size of 10. Small sample size. There's the first time. Now, take another random sample of 10, and it's over there. The average is somewhere else. Take another sample to get a different answer. Fourth random sample, get something else. Okay. The point is, every time you repeat a clinical trial, you're guaranteed to get a different answer. Guaranteed. Every single time you get a different answer. How do we cope with this? Well, one way of thinking about it is, if we repeat the clinical trial an infinite number of times, then we get something that looks like a bell-shaped curve. Okay, so here's an example. So the first time, we get an average of 53.9. X bar. X bar is the symbol for a mean. So the average is 53.9, and the second sample, I guarantee you, 53.3. Different distribution, 46.7. If we repeat the clinical trial an infinite number of times and take the average, and we put the averages in a histogram, we get this bell-shaped curve. Okay, we know this as a normal curve or a Gaussian distribution. So the feature is the average of the averages is the average, and that's centered right here in the middle of this bell-shaped curve. And then it gives you, the sampling distribution gives you all possibilities. This is important to when after the break, we go look at t-tests, because the t-test is based on the sampling distribution of means. So the sampling distribution of means gives us all possible means from all possible experiments, from very rare ones to very common ones. It gives us all possibilities. Okay, that's called the sampling distribution of the mean, and it's entirely relevant to when we talk about t-tests and p-values, because the p-values are derived from the sampling distribution of the mean. Okay. And so one concept is, how do we measure the spread of these means, right? The spread, right? So we notice that there's a spread of means, right? 53.9, 53.3, 46.7, 46.6 is a spread of means. How do we measure the spread? We use the standard deviation. So the spread of means is then called the standard error. Okay, so we have all these means, all possible clinical trials. You take the average of the average is the average. Okay, so the average, and then the distribution, the spread of the means is called the standard error. So many times you'll see in reports or articles you read something called the standard error. The standard error, by definition, tells you about the spread of the means. It tells you how accurate, how spread out are the means from the middle. Okay, that's called the standard error, the spread of all the means. Okay. Bell-shaped curves. We'll go back to this later on. We'll talk about sampling distribution and t-tests. One thing to remember, okay, comes at about 95%. So 95% of all the observation underneath this bell-shaped curve lie between, and these symbols here, plus or minus 2 standard deviation, above and below the mean. So I'm using Greek symbols. Mean, the mu is the Greek symbol for the mean. The sigma is a Greek symbol for standard deviation. And what this cartoon diagram shows you is that 95% of all the observations under this bell-shaped curve, which is a sampling distribution mean, lie plus or minus 2 standard deviations. Okay, so that's something to remember now. Now, 95%. So now we're going to go on to confidence intervals. Okay, so common and rare. So how do we come up? You've already seen in the literature 95% confidence intervals, 5% type 1 error, what they call alpha. Alpha error is 5%, 95. Where do these numbers come from? What statisticians have done is we like to think about common and rare as terms of areas under the curves or percentage of values in the thing. So if a measure lies anywhere between plus or minus 2 standard deviation, it is common because it occurs 95 out of 100 times, right? Plus or minus 2 standard deviations, 95% of the observations. Okay. A measurement, if we take a random number out of that centerpiece, that's 95 out of 100 times. So 90 out of 100 times, 95% of all the observations lie between plus or minus 2 standard deviations. So if 95% of the observations lie between plus or minus 2 standard deviation, it means that 5% lie outside that. So you notice that two numbers that you've seen time and time again, 95 and 5, they add up to 100. This is not a coincidence. So 95% confidence intervals correspond to 5% alpha levels, and it has to do that 95% represents common values, and 5% represents the rare values. So that's where these numbers are coming from. Okay. So we know that by repeating our clinical trial many times, we get confused because we can't get the same answer. We're always going to get a different answer, and we don't know what is the correct answer, right? If you do, like, that one with the BMI, body mass index, repeated the experiment 10 times. Okay, two numbers were the same, the rest were all different. I don't know what to believe. I don't know what to believe. What statisticians have come up with is something called a confidence interval. So at least with 95% confident, okay? So a confidence interval, okay? With at least a certain level of certainty or confidence, we know where the true value lies. And that's the whole purpose behind a confidence interval. Rather than being wrong 100% of the time, we're willing to be wrong 5% of the time. Okay. Confidence interval will capture the true value 95% of the time. Okay, and that's exactly what it says here, right? It says that if we repeat a clinical trial 100 times, 95% of the time, our confidence interval will capture the true value, and 5% time it will not. In statistics, 95% being certain is okay. On your tax forms, 95% being 95% certain that you have the correct income on your tax form, that's not the same. So in statistics, we can get away with a little bit of liberty here and saying, okay, we could be wrong 5% of the time. So 95% certain that the confidence interval will capture the true value. Very simply, it's calculated as a point estimate plus or minus critical value, standard error. Let me break this down. Point estimate, we'll start off with the mean. Okay, that's the average, the mean. The critical value is a special number that splits the bell-shaped distribution into common and rare values, right? Remember, 95% values are contained within plus or minus 2 standard deviation. What is that number? What is that number that divides that distribution between common and rare? That's called the critical value. Okay, that sets the level of certainty. And of course, this number here, the standard error. The variability, standard error, the variability in all these means. Okay, so you need some level of variability. How variable is your point estimate if you repeat your experiment multiple times? We need to capture that amount of variability. So we have level of certainty and some variability, and those are the two components that create the confidence interval. Another way of thinking about confidence intervals is a horseshoe, which may be familiar with you. So you think about the population parameter. That's a true value. That is totally unobserved. It's out there. It's unobserved. We're trying to estimate. What is our best guess at the true value? And the sample mean is our best guess. But we can't, by repeating the experiment, we can't be at all confident in our sample mean. So we use a confidence interval. A confidence interval are like these horseshoes. Okay, so you have the true value, and you toss your horseshoes towards the true value. 95% of the time, the horseshoe will be around that peg, and 5% of the time it will not. Okay, so what I mean by throwing horseshoes, that's your random sampling. That's like repeating your experiment multiple times. It's like tossing a horseshoe. So each time you do an experiment, you throw your horseshoe, and you hope your confidence interval is going to capture the true value. 95% of the time, you are going to get that horseshoe around your peg, and 5% of the time you're going to miss. So here's the cartoon example showing the population mean sitting in the middle, and it's showing 25 experiments, of which 24 of the experiments captured the true value, right? Meaning the confidence interval contained the true value, and one of them did not. Okay, so this is how we understand confidence intervals. Okay, as an example from literature. So if you're already reading literature, you would have encountered this phrase here. Okay, so here we have serum, very simple, serum vitamin A and zinc levels, healthy population northeast Thailand. And this phrase here, right? The average serum vitamin A level of the population. Okay, notice, I warned you, people misuse this phrase. Not everybody in northeast Thailand had their vitamin A levels measured. Man, that's impossible. Not everyone. But, so the correct phrase here would have been the average serum vitamin A level of the sample, right? You know, northeast Thailand does not have 744 people. It's much larger than that. It probably has millions. So you notice how these authors have misconstrued the truth already by calling it a population. So the average serum vitamin A level of the sample, 744. Now, 2.3 micromoles. That's the best guess. So 2.3 micromoles per liter, that's your best guess at the true value, and then 95% certain that it could be as low as 2.25 or greater than 2.23, and we're 95% it's going to capture that. Okay, so that's an example of this. The formula for the sample size calculation, notice that this is the average, sample mean. This breaks into common and rare values, and then the standard error, by definition, is the standard deviation, which is the variability in the sample by the sample size. So, a couple things. If we increase the level of confidence, say from 95 to 99, we just made the horseshoe larger. So, of course, we'll capture. If you want to be 99% certain, just make the horseshoe larger. It will capture, increase the significance confidence level. More variability. If there's a lot of variability in your data, if there's a lot of variability in observations, you can have a very large confidence interval, makes it wider. So one thing to look at is when you're looking at an article, paper, and reading a report, and you see a wide confidence interval, you have to think about, okay, maybe the standard deviations, maybe there's too much variability in the data, makes a very wide confidence interval. Or sample size. If the sample size is too small, it's going to make a very wide confidence interval, less precision. I think, couple questions here. Principal investigator, in consultation with the trial statistician, decided to increase the number of patients. So, increasing the number of patients, is it going to make your confidence interval wider or narrower? Good answer, narrower. And okay. Yeah, exactly. Yeah. Okay. That's why statisticians insist on having large sample sizes. Okay. Short confidence intervals are good because they narrow the range that the possible mean, true mean, right? It narrows the range of possibilities, and that's a good thing. Wide intervals are bad because then you have greater uncertainty about where the true value is going to lie. We're going to change gear here, and as I mentioned before the break, looking at inferences now, p-values, we cover confidence intervals using students' t-test as an example. To start off, here's an example. It's not a clinical trial, and I'll explain why it's not a clinical trial. Sometimes it's important to look at other studies besides clinical trials, and again, part of this is some of the stuff I've done for public health, identifying subgroups that are important that may be used to plan future clinical trials. So here's a study looking at racial differences between acne onset in females. So here we have, it's a cross-sectional study published in the journal Clinical Anesthesia and Dermatology back in 2014, looking at a diverse sample of women in the United States and looking at women who were between the ages of 25 and 45 with facial acne and looking at the onset. Now you notice that descriptively, among those who are the white Caucasian race, I have 107 women who are white Caucasian. The average age of onset they reported was 14.8 years, the age of acne onset, whereas in the non-white Caucasians, there's 101 of those women, were 17 years. Now, the reason why this is important is in designing a clinical trial, and if you find a intervention that is effective in preventing acne, you notice that the age difference at the age of onset is very different. So first of all, if you're designing a clinical trial looking at that onset of acne, you may want to select younger women if you have primarily white Caucasian, and older women if you have non-white Caucasian. Also, if you find intervention that's effective, your marketing strategy is going to be very different among the younger teenagers, which is age 14.8 years, versus the older teenagers, which would be 17 years. So again, not all clinical trials, even though clinical trials are considered gold standards, there's a lot of information to be gained from non-clinical trials. Now, also they report the mean and median. We notice that the mean age of onset is 14.8 versus 14 for the median. 17 years, the mean is 17 versus the median is 15. We know that the average age of onset of facial acne is right skewed. The distribution is right skewed. Notice that if you want to make everybody happy, you don't always have to choose between the mean and the median. Nothing wrong, as this publication shows. You can report both the mean and the median and keep everybody happy. Now, the one thing you should notice here, we're comparing the age of, is there a significant difference between the age of acne onset in both in white Caucasian versus non-Caucasian, and you notice a p-value of 0.0163. You may already know this, that this is a significant p-value because the p-value is less than 0.05. But we're going to unpack this example and look at how actually this p-value is calculated and what it actually means, and look at a different interpretation of a p-value that is not as commonly used. In terms of how we do hypothesis testing in statistics, we, just like any clinical trial, this is not a clinical trial, but we have a research hypothesis. We say that the age of onset occurs earlier in white Caucasian women than among non-white Caucasian women. We can come up with these research hypotheses based on observational studies, other type of surveys. In clinical trials, often we divide these research hypotheses based on, say, phase 1 and phase 2 trials, where we do animal studies, laboratory studies, and we say, oh yes, we've seen some differences, now we want to move on to phase 3. So we actually, when we conduct a study, we already have a hunch, and that is a research hypothesis. Now, how we construct a test statistic, we collect the data, which is the evidence, and determine whether the claim is convincing and put limits on the chance. So all we do in hypothesis testing is rule out chance. So we collect our data, we look at the opposite, we do some analysis, and then we try to rule out the chance finding. We have two different hypotheses in statistics. We start off with the null hypothesis, which is recognized as H naught, H subscript 0. It means there's no difference. Okay? It's called equipoise. In clinical trials, this is equipoise. When we recruit our participants, we say, we want to find out if our drug works. Even though we have a phase 1 and phase 2 trial that suggests it works, at a phase 3 stage, we still tell our participants we're uncertain. That's why we want to enroll participants, because we are uncertain. That's driven by the null hypothesis of statistics. In statistics, we start off as saying there's no difference between two groups, whereas the alternative hypothesis says there is a difference. So when we do inferences, we make the decision between whether or not we support the whether the data supports the null hypothesis of no difference or supports the alternative hypothesis of a difference. Okay, so these are the steps that we go through in conducting a hypothesis test. We specify a hypothesis, significance level alpha. You may be already familiar with this 5% alpha, so I'll go into a bit more detail shortly. The test statistics was basically used to rule out a chance finding. We start off by obtaining data, and that's why it's in orange. That's where we start off, obtain our data. We calculate a p-value, which we'll go through some details about where that comes from. And then the rule that most are familiar with is the p-value is less than the significance level alpha. We reject the null hypothesis. If it's greater, then we do not reject the null hypothesis. The test statistics. The hypothesis testing is very similar to the criminal justice system. It's conducted by argument by contradiction. In the criminal justice system is you're presumed innocent until proven guilty. So that's how it's, so essentially when statisticians first thought about conducting hypothesis tests, statisticians went back to what was familiar to most people is the justice system where you're presumed innocent until proven guilty. Okay, so how does that work? Well, in a criminal justice system, which might be much more familiar, is you have the accused in the courtroom, they're presumed innocent. And then the prosecution presents the evidence. And then you have sufficient evidence. If there's sufficient evidence, the jury will then say, this person is guilty beyond a reasonable doubt. Okay, the person is guilty beyond a reasonable doubt. There is no definition of reasonable doubt in the justice system. Everybody on the jury has a different threshold for reasonable doubt. In statistics, reasonable doubt, our measure of reasonable doubt is our alpha level, is our significance level. Okay, so mapping our errors. Okay, so some of the words we use in statistics is like type 1 error, type 2 error. The best way to think about it is mapping onto what's much more familiar to everyone is the justice system. So for example, if a person is truly innocent, okay, if the person is truly innocent and the jury says the person is guilty, okay, then they made a type 1 error. Okay. If the person is truly innocent and they said they're guilty, it's a type 1 error. In statistics, if there is no difference between the drug and placebo and we conclude there's a difference, we make a type 1 error. Okay, so 5% of the time, that's alpha. So 5% of the time, we will conclude a drug is effective when it's really not. That's what we mean. That's our chance. That's our chance. We have a 5% chance of concluding the drug is effective when it's not. That's called a type 1 error. A type 2 error is in a justice system where a person's guilty and really the jury says is not guilty, and that's a type 2 error. Okay. In statistics, a type 2 error is we conclude there truly is a difference. The drug is effective. The drug is truly effective, but we conclude that it's not. That's a type 2 error. Now, so the two things we juggle in statistics, and statisticians do this for calculating sample size, the type 1 error, okay, that's set at 5%. 5% of the time, we're willing to be wrong 5% of the time in saying the drug is effective when it's not. And then we look at power. Okay, we want to be 80% certain. Okay, statisticians use 80% as power, and we say we want to be 80% certain that if the drug is truly effective, we will make that conclusion, that it's truly effective. That's the correct answer, the correct decision, and that's called power. Now, in terms of significance and power, okay, so alpha, okay, that is our significance level. It's called alpha. A statistician will call it alpha. It's a type 1 error. the mathematical definition is the probability of rejecting a null when a null is true, meaning that the probability of concluding the treatment is effective when it's not. Okay, it's set to 5%. You may know already. It's called the significance level. What it really literally means, people kind of throw around this alpha, 5%. It means that there's one chance in 20. Okay, if you take 0.05, that's one chance in 20. One chance in 20 of concluding something's going on when in fact nothing's happening. That is, in other words, one chance in 20 of concluding that the drug is effective when it's not. Mapping it back to the criminal justice system, 5%, that's a reasonable doubt. Okay, that's our threshold. That's why we say p-value is less than 0.05. That's significant. That's our threshold. We've set our reasonable doubt threshold at 5%. Okay, and the last one there is p-value is less than 0.5. We reject the null hypothesis. Okay. So, statistical significance and p-values. We'll just focus on this period right here. Okay, the tail area is called the p-value. So, what we did before the break is a sampling distribution, all possible means. The p-value is calculated as the tail area. Okay, the tail area is called the p-value. That's where we get the p-value from. All the sampling distribution of means, we get the p-value. Now, the practical definition that I want to leave you with. Okay, there's a lot of theoretical stuff, but the practical definition of a p-value. If we observe or conclude something's going on, how likely could have this occurred by chance alone? That's a slightly different understanding of a p-value. Okay, from what is commonly done, this p less than 0.05, significant, p greater than 0.05, non-significant. If you start thinking about p-values as a chance occurrence, you're going to be much further ahead. Okay, we'll see how this works. Certain thresholds, we think about p-values. I like to think about p-values more of a chance occurrence. Evidence. Mapping it back to the criminal justice system, evidence. So basically, we're often here is if the p-value is less than 0.5, then it gives you moderate evidence. But there's other levels of p-values, right? If the p-value is much smaller than the strong evidence, and if you have p-values less than 0.0, very strong evidence. Okay, so again, just to say that the p-value is less than 5% or 0.05 is insufficient. You actually need to start looking at how big or how small that p-value is. If the p-value is very small, it gives you very strong evidence against the null hypothesis. Remember, the null hypothesis says there's no difference. So a p-value that's very tiny says there's a lot of evidence against no difference. Whereas if the p-value is large, then there's little evidence against no difference. Okay, so in this slide is sort of technique of some of the calculations to get the test statistics. So essentially, specify null and alternative hypothesis. The first one says there's no difference versus it's a difference. Okay, that's clear cut. You set the alpha level, reasonable doubt. That's our threshold. 5% is a reasonable doubt. And then we construct a test statistic. Now, a couple features. This is an applied, webinar, but there are a couple features about the test statistic. There's a mystery about how does this p-value come about. Okay, the test statistic is simply constructed as the difference between the two means, right? The average age of onset of acne. Okay, difference. So you have a difference on the top, and then you say, okay, now we have a difference from a single sample. If we repeated this survey multiple times, we're going to have multiple differences. Just think about the clinical trial. Difference between a drug and a placebo. You get a mean difference between drug and placebo. Each time you repeat a clinical trial, you're going to get a different difference. And it's going to vary from sample to sample to sample to sample. What is the measure that measures the variability among all these differences? That's the standard error. So the test statistic is really a ratio between what you observe and the measure of the variability of all possible experiments you can do. So essentially, I like to think of the test statistic as a ratio between signal and noise. Signal is the difference you observe in your study, and the standard error measures how much variability you have from sample to sample to sample to sample. And the more variability, so notice where the variability is, it's in the denominator. The more variability you have from sample to sample to sample, the smaller the test statistic. Okay, so that's really key. The smaller, the more variability you have, which is a larger standard error, it's in the denominator, the more variability you have, the smaller the test statistic. Okay, so again, the test is a ratio between what's observed and how much variability there is from experiment to experiment. Now, all test statistics are exactly like this. It's a signal to a noise, no matter if you're comparing means, proportions, rates, whatever you're comparing is always that kind of format. Okay, so here is a cartoon illustration of a sampling distribution of all possible mean differences. Okay, it's centered at 0, meaning there's no difference. And now you take your sample. Now we notice that the mean difference in acne onset is 2.2 years. And we want to know, the test statistic is formed to say, okay, does it fall in the common range or in the rare range? Okay, so we define the common range as plus or minus 2 standard errors, plus or minus 2 standard deviation, which is in the middle. If our difference falls in this middle piece, then we say it's too close to 0. That's what we're using for, is how far is our observed difference from 0. The further away is from 0 means it can't be 0. Remember, argument by contradiction. I'll repeat that. If our mean difference is far away from 0, then we have to say there is a difference. Okay? And so our threshold is set at this 95% level, where we have 5% tail at your end. So notice that the 5%, that's set out here, right? The orange, highlighted. So if our test statistic and our mean difference lies in the orange areas, then we say it is far enough from 0 beyond reasonable doubt. I'll repeat that. If our test statistic and mean difference falls in the orange areas, it is far away from 0 beyond reasonable doubt. And because it's beyond reasonable doubt, we can reject the null hypothesis and say there is a difference. Okay, that's how it works. Now, the p-value. The p-value, as I mentioned, is calculated as the tail area. It's how much reasonable doubt you have. So the area from the test statistics over is the exact measure of your reasonable doubt. That is your chance occurrence. That tells you how far, right? We know the test statistic falls in the orange area, but how far? What's the measure? The p-value measures how far you are in terms of probability from 0. So we have, in both cases, 0.00819. That's our area under the curve. And that is, we add those two numbers together and we come up with a p-value. Okay, so that's our exact measure of chance. How far are you from 0 in terms of probability? And that is the p-value. Okay, so we add up the two areas and we get 0.0164. And so by convention, we reject the null hypothesis. Many would just stop right there and say, okay, we have a significant result. There is a significant difference between white Caucasians, non-white Caucasian women in terms of age of onset, and we'll stop. Many people just stop there. We can always do better. Okay, we can now understanding that this number here is a measure of chance. It measures how far your difference is from zero. We can start interpreting in a slightly different way. Okay, so as before, there's no difference, and of course the difference is between 2.2. Okay, so that's well known to most people. This is another way of thinking about it, a better way. There's always a better way, and this is the better way of thinking about p-values. And I'll read it. By concluding that the mean age when acne started is different between white Caucasian women and non-white Caucasian women, there's a 1.64% likelihood that this observed difference could have occurred by chance alone. Okay, so rather than considering a p-value just greater than or less than a 0.05, when we convert the decimal number to a percentage, it actually represents the likelihood of a chance finding. So there's a difference of 2.2, and it's only there's a 1.64% likelihood it's a chance finding. It's a small chance. And because it's a small chance, it must be a real result. Okay? So please do remember that you convert the decimal to a percentage number, and now you're speaking something that is much more meaningful than this threshold for reasonable doubt, which is less than 0.05 or greater than 0.05. Now you can actually interpret this in terms of a likelihood of a chance occurrence. So if it's less than 5%, we say it's real. If it's greater than 5%, we can't rule out chance. Confidence interval around a mean difference, we can actually calculate this. Before the break, we looked at a confidence interval around a single mean. We can calculate a confidence interval around a mean difference, the same thing here. We're trying to actually capture the true value. We can say that even though the average age of onset is 2.2 years, the age of onset difference could be as large as 4 years or as small as 0.4 years, okay? So that gives a possibility. Our best guess from a single study is 2.2 years on average. But it could be as large as a 4-year difference or as small as a 0.4. That range, that confidence interval around a difference gives you a range of possible values for the true difference in terms of age of onset of acne. All right. So the other thing the confidence interval around a difference can do is a bit of hypothesis testing, inferences. So given that this range, -4 to 0.4, remember 95%, those are the common values. Those are the common values. So what this says is if the common values, if this range is the common values, then everything outside that range is uncommon, it's rare. If the confidence interval around the difference contains 0, if 0 is a possible difference, it's not significant. If 0 is not in this range, then it's not possible, and therefore you can conclude significance. There's no difference. Okay? So another way of thinking about this is mapping onto p-values. Okay? A confidence interval around difference has a 1-to-1 correspondence to p-values. So here in the middle is 0. Okay? So 0 means no difference. So here we see that the confidence interval does not overlap 0 and the p-value is significant. So if the 95% confidence interval around the difference does not contain 0, then the p-value is also significant. If the confidence interval contains is close to 0, we notice that its p-value is 0.005, which is close to the threshold of reasonable doubt. And of course, if the confidence interval around the difference actually contains 0, then it's non-significant. So there's a one-to-one correspondence between a confidence interval around the difference and the actual p-value. So articles that report confidence intervals around differences, you can actually look at that and say, yes, if it contains 0, it's significant. It's not significant. If it does not contain 0, it is significant. So one of the things I want to leave you with as well, you say, okay, can I do any of this to myself? Do I need to take another stats course? Do I need specialized software? What can I do for myself using what I've learned today? Well, up here is a package called QuickCalcs. It's actually supported by GraphPad, which is a package you can download. But QuickCalcs gives everybody the ability to do statistical analysis very simply online on their phone, on their laptop, anywhere they wish. Here's the URL, www.graphpad.com, QuickCalcs. And I'm just going to go through an example, reproducing the results I just showed you. So within QuickCalcs, continuous data, again, you have to select. There are different types of, they have categorical data, continuous data. Here we have continuous data, and we want to do a t-test to compare two means. It's user-friendly, and you can actually do this on your own. Okay, so interact with the t-test calculator. The nice thing about QuickCalcs, I get no royalty. I'm not supporting them. I'm not giving royalty. I'm just showing you a way to actually do your own basic analyses without always have to go to a statistician or doing it in Excel, which is inefficient. This is a good way to actually be able to do some basic statistical analyses. So it allows you, QuickCalcs allows you to choose whether or not you want to enter data. Okay, you can enter raw data, or you can enter the mean, standard deviation, and the sample size. Okay, and that's what I did here. For example, I entered white, non-white, the two means, two standard deviations, and a sample size. I've selected an unpaired t-test, which are two different groups, and it gives you an answer. Okay, it tells you the two-tailed p-value equals 0.015. It tells you it's significant, and also gives you the 95% confidence interval around the difference. And it gives you also the test statistic and also summary of data. So this is a great little online module or package, you want to call it, to do some very basic statistical analysis on your own. If you get the mean, standard deviation, sample size, you can actually do these analyses on your own. I want to make a comment about statistical significance and clinical importance. Again, two ideas, two phrases that get interchanged incorrectly. Okay, statistical significance is all about ruling out chance, right? Difference between groups does not pass the threshold. That's what statistical significance is. If the p-value is less than 0.05, you reject. If it's greater than 0.05, you did not reject. Okay. Statistical significance does not take into account the size of a difference. Okay? Sometimes you might find that you find no statistical significance. Your test statistic does not pass the threshold of 5%, and yet you observe this large clinically important difference. Statistical significance tells you nothing about the size of the difference. On the other hand, what you might find is you have a study that your statistician says there is no significant difference, and yet you look at the results and say, wait a second, I see big differences between the two groups. Okay, so two clear distinctions. Statistical significance tells you nothing about the importance of your finding, whereas clinical importance tells you nothing about this significance. So they actually go hand in hand. They sometimes are used interchangeably because you say, oh, I found a significant finding. Which is it? Is it statistically significant or is it clinically important? You need to make that clear distinction. So here we have a study. We're going to go through together here. So a randomized study of intravenous hydromorphone versus intravenous acetaminophen in older adult patients with acute severe pain. And so we had here is a randomized study, and they compared, just going briefly through here, 1,000 milligrams of intravenous acetaminophen to 0.5 hydromorphone. So acetaminophen to hydromorphone, and we want to look at pain. 162 participants, and what they assessed was primary outcome was improvement on a pain scale, 0 to 1, ordinal scale, 0 to 10 pain scale, a baseline in 60 minutes later. Okay? And this is really important. In this article itself, they define what a minimal clinically important difference. Okay? So they define that on a scale from 0 to 10, an improvement of 1.3. So that's a number you need to remember when we look at further on the other slides. A difference of 1.3 was considered to be clinically important. Okay? So it may be significant or not, we'll find out very shortly, but the clinically important difference, they would say, an improvement of 1.3 on a pain scale would be important. Okay, so again, two groups, 100 milligrams intravenous acetaminophen, 0.5 milligrams intravenous hydromorphone. 60 minutes later, they looked at the pain scale, where 1.3 is a clinically important difference. Okay. So here are the results. Okay, 60 minutes. Patients taken acetaminophen improved by 3.6, whereas patients taken by hydromorphone improved by 4.6. And we have a 95% confidence interval. Okay, the difference between 3.6 and 4.6 is 1.0. That's an easy subtraction. And the confidence interval, 95% confidence interval, the report is 0.1 to 2. So is the difference in mean improvement between the acetaminophen hydromorphone groups? Okay, which choice is it? Give you a bit here. Think about this. Okay, and any guesses? Okay, statistically significant and clinically important. Okay, so let's break down the answer here. So, a couple things. The mean difference is 1. Okay, the mean difference is 1. So, again, making this clear distinction between clinically important and statistically significant. So, these authors pre-specified that unless the difference was greater than 1.3, it's not clinically important. Okay, a few studies actually pre-specify a clinically important difference. These authors did. So if we don't see a difference of 1.3, we don't consider that an important difference from the patient's perspective. So let's have a look. Okay. Now, the difference is 1. Okay. The mean difference between 3.6, right? 3.6 acetaminophen, 4.6 hydromorphone, difference is 1. So the difference is not clinically important. Yet, when we look at the confidence interval, the confidence interval around the difference does not include 0. Okay, notice there's no p-value. These authors did not. I did not fool you. I'm not fooling you. I did not remove the p-value. These authors did not report the p-value. These authors just reported the mean difference and a 95% confidence interval. There's not a single p-value in the entire article. We look at the confidence interval around a difference. We see, yes, it does not include 0. It is statistically significant. So here we have here we have an example where we have statistically significant because it does not include 0. Okay, we have a significant result. Who cares? We have a significant result that who cares, because it means nothing to the investigators. It means something to the statistician because we have a statistically significant result because it does not include 0, and yet the difference is not of clinical importance. So there's the distinction between statistical significance and clinical importance. They don't always go hand in hand. Okay. Now, in terms of getting the p-value, okay, there is no p-value. We want to know what the p-value actually is. And so we can actually go to quick calcs and the two-tailed p-value by just putting in the numbers right in here. Okay, the two means, two standard deviations, and sample size. They gave us the two means. Okay, we'll look at them again. Okay, there's the two means, one mean, two means. They even wrote out the standard deviation, long-term standard deviation, and of course the sample size they gave us in the article. So based on the two means, two standard deviation, and sample size, they didn't give us a p-value, but we can actually calculate it, and we find a p-value 0.041, and the difference is 1, the clinically important difference of 1.3, so it's clinically not important, but we have significance. Okay, so how do we interpret the p-value now that we know what it is? One happy face, two happy faces. Great, yes, exactly. See, you got it. You got it. Okay, a 4.21% likelihood the observed difference between the two drug could have occurred by chance alone. You notice in the previous example we had a p-value of 0.0146 in that acne example. See, both those p-values are less than 0.05, but they don't hold the same value. Both results, the acne example and this pain example, both of them had p-values less than 5%, but they don't hold the same value. This is a 4.2% likelihood. The other one had a 1% likelihood of a chance finding. Okay, so again, thinking about p-values in terms of percentages will get you much further ahead than just thinking about this dichotomy of significant, not significant. Adverse events. Okay, so this study reported adverse events. So adverse events were reported in 7% of patients taking acetaminophen, 12% in those not taking ones, and of course, no p-value here, no p-values. All they report is a 5% difference and a confidence interval around. So give you a moment here to think about, is there a difference? Is the difference is between two groups? Okay, we got one happy face. And I've got a hand up now. Okay. Okay, think about the confidence interval. Look at the confidence interval. Does it include 0? Does the confidence interval around a difference include 0? If it includes 0, it must be something. Okay, give me a moment. Okay, so first of all, if you look at a confidence interval, it says a difference. Confidence interval around a difference, so it's slightly different. Not the means, but these are percentages. But a confidence interval for a difference. You notice that the confidence interval from -4 to 14%, it includes 0. So as soon as the confidence interval around the difference includes 0, it is not statistically significant. Okay, so that one's there. Okay, could be this one or that one, right? Now let's look at the other piece. A difference of 5. Okay, even though there is no statistical difference between the groups, do you really want to deal with, you look at this and say, well, if I take acetaminophen, if I take hydromorphone, okay, there's a 12%. There's a 12% adverse event rate versus 7%. So this is an example where it's not significant, statisticians will say there's no significant difference, but from a clinical perspective, there's a 5% difference. Hydromorphone has a 5% increase in adverse events over acetaminophen. Who wants the adverse event? So even though it's not significant, it may not matter if you have more side effects. So again, another clear example of how statistical significance or non-significant is different from clinical importance. So you have this dichotomy in the two examples. Okay. And we can actually calculate, use quick calc. You notice that the p-value is 0.2922. P-value, we can use quick calc to calculate these difference between two proportions. Okay, so let's kind of look at some of the other methods here: analysis of variance, linear regression, chi-square test, logistic regression, survival analysis, and then we have open for questions. So, few methods. So, common statistical methods that you'll come across. I'm not going to go through all these in terms of detail, but these are the common ones that statisticians will use to analyze data, and I'll go through them briefly. Now, all frequent statistical tests use p-values and confidence intervals. So we spent quite a bit of time on looking at confidence intervals, understanding what confidence intervals are, how to interpret confidence intervals. We spent a little time about what p-values are, where the p-values come from, all that stuff. The fact is, whether you're using t-tests, chi-square tests, any of these methods, p-values and confidence intervals are interpreted in identical ways to what you learned in terms of mean, confidence interval around means, and confidence interval around mean differences and difference in proportions. They have the same interpretation. So whether you have a p-value from a t-test, a chi-square test, regression analysis, survival analysis, whatever application is, take your p-value, create a percentage, and interpret it as the likelihood of a chance finding. The same thing with the confidence interval. If the confidence interval contains 0, you know it's not significant. There's no significant. If the confidence interval does not contain 0, you know it's a significant result. Okay, so even though we only dealt with the t-test, the interpretation of the confidence interval and p-value applies to all these methods. So just briefly, the chi-square test assesses difference between two groups or more for binary outcomes. So a t-test compares two continuous outcomes. So two binary outcomes, you use a chi-square test. 3 more groups. A good example is a dose-finding study. We have placebo and 2 doses. We use analysis of variance. Very similar. It's an extension of a t-test, so because comparing 2 or more groups on a continuous outcome, particular means. Linear regression is when you want to look at the relationship between 2 variables. And all these I'm going to show you an example very shortly. Then we have something called logistic regression. It's an extension of comparing 2 proportions. You have a binary outcome and you have a set of predictors. So the logistic regression is an extension of comparing 2 proportions. Repeater measures. Many of the studies in clinical trials follow participants over time. And so you have multiple measurements over time. In this case, we use something called repeater measures. And then finally, time to event survival analysis, when you want to look at time to an occurrence of event. Rather than looking at whether or not an event has occurred or not, you're now looking at when it actually has occurred. And I'll show you an example of that. Linear regression. So here's an example from literature, and in each of the examples are taken from literatures. So here's a relationship between a child's age. So we know I look at a child's age and their hemoglobin A1C. And we find that as a child ages, so we're looking at years, so we start off with 0 years on a horizontal axis up to 12 years. And we notice that as child's age, their hemoglobin A1C increases, okay, with children with type 1 diabetes, okay? So this is a method okay, called regression analysis, looking at two continuous measures. Child age is continuous, hemoglobin A1C is measured, and now we're looking at the relationship, and we can actually see that there is a positive relationship, basically saying as children's age, the children with type 1 diabetes, as they age, the hemoglobin 1AC increases as well. We use regression analysis for that. Here's an example of logistic regression. I'm going to throw out a phrase called odds ratios. You may see that when reading in a report or an article. And so this is basically looking at the relationship. Purpose of logistic regression was to estimate the association between surgical acuity and a postoperative cardiac event and days from surgery, 30 days from surgery. So looking at different ways of doing surgery. So two different ways of doing surgery: elective surgery or urgent and emergent surgeries. And we see the cardiac risk. So for example, we see among the patients who had elective surgery, the cardiac risk was 3.4 per 1,000. And among those who got urgent and emergent surgery, the cardiac risk was 28.7. You divide those two numbers to get something called the odds ratio. What's the odds, right? What's the odds of having a cardiac event if you get urgent and emergent surgery versus elective? Okay, so that's what we use logistic regression for. We're looking at the relationship. We're looking at the relationship between the type of surgery and a cardiac event, which is binary. You either have a cardiac event or not. We use logistic regression to actually assess the odds of having a cardiac event when you have urgent and emergent surgery versus elective surgery. In statisticians, we use logistic regression to actually measure that association. Repeated measures. So here's an example looking at blood pressures over time. So we have time measurement from 1 hour to 3 hours, 1 minute, 0 minutes to 180 minutes, which is basically 3 hours. And then we're looking at heart rate. What happens? What happens to your heart rate after you take dietary protein? So, and we measure over time. So repeated measures, by definition, repeated measures saying you're taking continuous measurements. So here we have heart rate was measured. Okay, heart rate was measured with an automated device every 3 minutes over 3 hours. Okay, so older men were given 3 different interventions. They're either getting 270 grams of whey protein, 30 grams of whey protein, or non-caloric control. Okay, so here we are. 70 grams, 30 grams versus nothing. Now you're looking at heart rates over time every 3 minutes. That's what we mean by repeated measures. The same measurement is being taken on the same individual over time every 3 minutes, and we plot this out. So we notice that among the controls, right, the control group here, basically flat, as expected, right? Your heart rate stays stable. You know, okay, there's some fluctuations over 3 hours, but basically your heart rate stays stable. Among the men who got the high caloric rate, okay, got 70 grams, you notice that their heart rate actually increased. Okay, this is what we do in repeated measures. We measure the individuals over time. This is a graphical display of what happens to the heart rate. Each of those dots, each of the dots is their heart rate over 3 minutes, and we use repeated measures to display these data and analyze the data to show that there's actually a difference between a dose-response relationship between the amount of protein you have and your heart rate. Time to event analyses. Okay, so here we have the effect of marital status on the survival of patients with multiple myeloma. Interesting question. It's saying, okay, what is a person's trajectory. Okay, if a person is diagnosed with multiple myeloma, what is their overall survival? Different statuses. Okay, so they compared. Okay, so all these patients had multiple myeloma. Some were married, some were divorced, some were single, some were widowed. And we use time to event analysis. So we use time to event analysis to see when they actually pass away. Okay, so we look at these different curves, and we notice that in each. So this line here, the bottom one, are the widowed. So they have the worst prognosis. So what this means, we can look at these data and say, okay, patients who are widowed have the worst prognosis if they are diagnosed with multiple myeloma, whereas individuals who are married have the best prognosis. And so we actually can look at this, the 5-year overall survival rates. Okay, the overall 5-year survival rates, if you are married, you have a 46% chance of survival. If you are widowed, you only have a 24% chance of survival. So we can actually use survival analysis to actually look at survival times over time. Another way of looking at it, again, a phrase you hear is a hazard ratio. So what we look at is saying, well, comparing to married, okay, which is the reference, married, how much more likely are widowed people to die compared to married? So comparing widow to married. So the risk of mortality, so we go back to the previous figure, we notice that the widowed patients have a worse mortality rate, okay, worse survival, worse mortality compared to the married. The way we quantify that numerically is to use something called the hazard ratio, okay? And here we see is patients who are widowed are 1.855 times more likely, higher likely to die, have the risk of mortality is higher, more likely to die compared to patients who are married. So it's much better to be married when you're diagnosed with multiple myeloma. Actually, it's not good to be diagnosed, period, with multiple myeloma. But those who were married had a better survival rate than those who are not married. So I wanted to do something called forest plots, subgroup analysis. So here's a study that looked at 2 drugs here, nab-paclitaxel and glucosamine, majority pre-spliced group. So the idea is most studies report overall. So among all patients, we noticed that if you got the paclitaxel, you did much better. Okay, we find that down here in this legend here. Paclitaxel is better than glucosamine, is much better, and there's 23% reduction in death. Hazard ratios, okay? Hazard ratio, 23% reduction in death, hazard ratio. One of the things you want to do is identify, these are called forest plots. Does it apply to everybody? We know that those who got this drug, paclitaxel, did much better. But did it apply to everyone? Well, we can start breaking it down. And this is what we call forest plot. This graphically displays these subgroup analyses where we can look at age greater than, yes, they did better, by males and females, okay? So again, something to keep at the back of your mind when you're working with statisticians or clinical trials, you say, okay, can you do a forest plot for me? And say, okay, I want to graphically display my results by these different subgroups because I want to know whether my intervention is effective in all these different subgroups, or did the intervention work better in some subgroups than in other subgroups? And what I mean by subgroups is, did my intervention work better in some individuals than in other individuals? Employ statistical terms used in clinical research. So basically, I'm going to recap what we've covered today. and then make a few comments about interacting with statisticians. So, what we covered in a nutshell: the mean and median, okay, the difference between a mean and median and what they mean. Standard deviation, interquartile range are both measures of spread, but slightly different. So, the mean corresponds to a standard deviation. Okay, standard deviation and mean go together. So you have the mean as your best guess of what's going on. Standard deviation tells you about the spread of the observations, whereas when you report the median again is your best guess at the true value, and the interquartile range is the measure of spread in the observations. Okay, they kind of go hand in hand. So when you see the mean, you often see the standard deviation. When you see the median, you'd often see the interquartile range. Next one here is the standard error. Okay, again, standard error measured the precision of the sample estimate. That's another way of thinking about it. Also is it provides you the spread of all possible means from all possible experiments. Hypothesis testing. Again, always remember hypothesis testing about a chance finding. Okay, chance finding. Confidence intervals. Gone through those. Tells you about, it gives you a level of certainty around your results. Remember, a single mean, you can't be certain at all. You can't be certain about a single mean or a single median. The confidence interval gives you a range of possibilities. And you'll see whether you report odds ratios or hazard ratios, they all have confidence intervals because they provide a single, it gives you a range of possibilities, level of certainty. And p-value, the likelihood of a chance result. Okay, again, try to get away from this idea that p-value is less than or greater than 0.05 and start thinking about p-values as the likelihood of a chance finding. Okay, alpha significance level, 5% effect size. Effect size, difference in estimates between two groups relative to their standard deviation. Sample size, statistical power, we talk about, a little bit about the type 1 error rates. And then if there's anything to leave you with, statistical significance for clinical importance, yes. Okay, just because a result is not significant, you may actually be onto a clinically important finding. Just because, and the adverse event, the side effect, the adverse event example is a great example where there was no significance, no statistical significance, but there was a difference, a 5% difference in adverse events. So regardless if anybody says it's not significant, you should not be taking acetaminophen over hydromorphone because it increases your risk of adverse events, regardless of the significance. Okay. And then, okay, last bit here. So working statisticians, some advice from somebody who's been working with colleagues for over 30 years. So bring them in as early as possible. Many times I find myself in a position where somebody calls me in because they've run into trouble with their data set, their analysis, their protocol. They submitted their protocol to the FDA and it got rejected, and they call me up, hey Misha, your experience, we need some help because the FDA just rejected our application, we need your help. Bad maneuver. Bring them in as early as possible, get them involved early, and you're less likely to get yourself in difficulties. When you're involving them in trial design, first of all, clearly articulate the research question. I spend quite a bit of time with my colleagues, my collaborators, trying to get them right down. What are your research questions? Often they have the exposure, the intervention, they know that, but what are they measuring? What is their outcome? What is the primary outcome? What is the secondary outcome? Is it a surrogate marker, biomarker? Narrow it down to outcomes. What are you trying to do? Okay, and be very clear about this. A different type of trial designs. Investigators don't know all the trial designs out there. There are Generally, there's a parallel group, the one-to-one randomization, which is common. But many investigators forget you can do 2-to-1 randomization, 3-to-1 randomization. You can do also crossover designs. There's adaptive designs. They're all different types of designs that are out there. Don't always get stuck with the one-to-one parallel group blinded design. That's boring. There are other type of designs that's much more effective. When you're coming to the statistician, you have the outcomes. What about the estimates? What do you think are your results going to be? Okay, statisticians need to calculate sample size, some level of estimate. So, for example, if you're looking at differences between blood pressures, what do you think the blood pressure is going to be at the end of the study in one group versus the blood pressure in the other group? Come back with some estimates. Most of the time it can be found in literature or from earlier phase studies, but we need the estimates to actually do any type of sample size calculation. Randomization, yeah. Again, was it 2-to-1 randomization, 1-to-1 randomization? There's something they call minimizations. Stratification factors, besides site, you're going to stratify by gender or age. These kind of things need to be considered at the randomization process. Sometimes I have to, debate with how many follow-up visits you want. You want 3 visits, 4 visits? Is it every 3 months, every 6 months? Having some sense of follow-up visits really helps in terms of designing the study and doing the sample size calculations. One step's quite often forgotten because statisticians are not database managers. Leave them out of it. Wrong. We get the output. We get the stuff. There's this phrase, garbage in, garbage out. Too many times I've been involved in studies where database managers do something and I look at it and say, gee, what do they do here? It's a mess. So getting statisticians involved with the database creations in terms of creating the variables, creating the skip patterns, things like that, is important. Okay, don't always leave it to the database managers to design your database. That's a bad practice. Discuss on trial monitoring stopping rules. Yeah, do you want to stop your trial early for futility or efficacy? Something many trials don't think about. Hey, time is money. Suppose you find a benefit early on. Don't you want to stop your trial early? If you have enough safety data, why continue enrolling patients if you know the results earlier on? So thinking about stopping rules and monitoring is very important. And then also, statisticians write cryptically. I write cryptically. It's always good to have somebody who's not a statistician review the statistical analysis plan for clarity, making sure it makes sense to the average reader. And also, the last thing here, be open to alternative methods of analyzing data. Too often what I find working with colleagues is they work in silos. Okay, they work in a particular field of area of interest, does things over and over again. I work in multiple fields, so I see different things. I work with oncologists, I work with stroke experts, child intellectual disability people, dietary people, things like that. So I see different fields. So I bring up different ideas from different fields, and it's nice to have work with colleagues that are open to new ideas, bringing from different ideas. And I think with that, I have a few minutes left. And questions? Open for questions? Yes.
Okay, this is Bandel. I just want to say thank you to Misha. This was a very detailed, comprehensive overview of statistics. I actually took statistics back in college, but I don't remember anything from it. And now that I work in this industry, I realize how critical it is just to, just have some sort of understanding of how this plays into clinical trials. And I have to admit, I got a little lost during the confidence intervals and p-value calculations just because there was just a lot of just information surrounding that. But I mean, overall, I thought the presentation was very well laid out, and you provided some great examples. And I like the interactive portion too, because it forced me to really, pay attention and just try to understand the rationale for the answers. But Also want to say thanks for providing the slides too, Stephen. I think that's a really good resource tool to have, and I'll certainly refer back to it in the future. But, no questions for me. Just want to say thank you for this great presentation.
Okay, well, thank you. Thank you for your comments. Anne has a question about how to power a study, clinical study. As a statistician, one of the most frustrating things I find is investigators come to me with no clinically important difference in mind. Powering a study is really a no-brainer because we set our type 1 error at 5%. That's the alpha level, and we classically set our power at 80%. So those things are fixed. 5%, 80%, that's fixed. The biggest problem I have is pinning investigators down to what they would consider a clinically important difference. And the other thing is, it's easy, they'll come up, even if I get a clinically important difference, it may not be actually feasible. So the best advice I can give you is, the first thing I ask, nowadays I've learned through trial and error, is what can they afford? What can the investigators or the study team afford to do? It's one thing for me to say, do a sample size calculation and say, well, you need 10,000 patients. It's not feasible. So actually, through many years of experience, I've actually started working backwards. And so I actually asked the investigators, how many patients can they enroll? That they know right off the bat. They say, well, based on our budget or based on our timelines, we can only enroll 500. That's where my starting point is. Then I start thinking about, okay, what can I do with 500? How large of a difference, or how large of effect size, or how large of a difference can I actually observe, can I detect with only 500 patients? From there, you can use different measures, okay? So rather than measuring, say, blood pressure as in hypertension, yes, no, if I use blood pressure as a continuous variable, I gain statistical power. So essentially, that's what I would say about powering a clinical study, is start off with what's feasible, and then look for a clinically important difference that actually, and measures, instruments or measures, that will actually fit that sample size. It's absolutely useless, in my opinion, to give investigators, study teams, and say, we need to study 10,000 patients, and get statisticians a bad reputation, gets them nowhere. Thank you for attending today.